Alright, let's talk about acids and bases. We're going to start with the basic definition that Arrhenius came up with. And Arrhenius, shown here on the upper right corner, basically describe a substance as being an acid if it did contain an H. Specifically, when you look at the molecular formula, the H appears first in the formula, followed by something else. So the fact that the molecule had an H is what made it potentially being an acid. And another way to look at it, which as you'll see in a little bit, we're definitely gonna be utilizing to a great extent, is that if you do have an H and you're an acid, you will be giving off H plus. Also, with the concentration of H plus, if you do take the negative log of the concentration of H plus, that yields the pH, which is a measure of how much H plus concentration you have and how strong an acid may be. One last thing to be said is that H plus in water ends up forming a hydronium ion, H3O plus. So you might see me refer to H plus as H3O plus or H3O plus as H plus. They're the same thing. So just be aware of that. Alright, Arrhenius also defines a base as a substance that contains a hydroxide. So if you have a metal hydroxide, then you are very likely a base. But it pretty much has to be a metal for this to work out. So for instance, if E was an H, that wouldn't qualify as being a base because water, doesn't give off hydroxide, at least not to a great extent. Alright, so anything that produces hydroxide, right? So, and also much like the pH, if you take the hydroxide concentration, apply the negative log to it, you get something known as the POH. Alright, so that's the Arrhenius definition. You either have an H plus or you have an OH minus, in which case you're an acid or a base. But then Bronsted and Lowry come around and they augment the definition somewhat. First of all, when they look at the acids, they say, well, an acid is anything that donates an H plus, produces an H plus, in other words. And in that sense, they don't really extend the definition of an acid. It's pretty much the same as that of Arrhenius. But a few things that do need to be said is that there are a list of acids that I do need you to remember. I need you to remember them as being strong acids in particular. I'll be depicting what that means in full detail a little later. But the list of 11 strong acids is as follows. You have chloride, bromide, iodide. If you just add an H plus to them, you get the hydrohalic acid. So hydrochloric, hydrobromic, and hydroiodic. All three of those acids are strong. In addition, if you add 4 oxygens to the hydrohalic acids, you get the perhalic acids. So perchloric acid, perbromic acid, periodic acid. And if you look once again at the hydrohalic acids and add 3 oxygens, you get the halic acids, which are chloric, bromic, and iodic. So all 9 of them, which can be derived directly by looking at the periodic table, chlorine, bromine, and iodine, all 9 of them are strong. And in addition to them, you just got to remember that sulfuric acid and nitric acid are also strong. If you remember these acids as being strong acids, then by default, anything else that I give you that can be an acid is going to be considered a weak acid, right? So hydrofluoric acid, water, bromose acid, hypobromose, hydrosulfuric acid, any other acid, even citric acid, ascorbic acid, acetic acid, everything else that is not part of the 11 acids that I told you to memorize will be considered a weak acid. Alright, so definition of the acid is not all that different from that of Arrhenius. But here's the part where they definitely expand the territory. Instead of thinking of a base as something that produces hydroxide, they look at it yet again from the point of view of the proton. And they said a base is anything that accepts an H plus. An acid donates H plus, a base accepts H plus. And when they do that, they extend the definition to containing not only hydroxide as the base, but now anything else that can take up a proton could potentially be a base. Specifically, ions that are highly negatively charged, and if they have lone pairs available, they can behave as bases. So carbonate, hydrogen carbonate, phosphate, oxides, all of those can behave as bases now. And now the repertoire has been increased by changing the definition ever so slightly. All right, so if you look at the following equation, technically what happens is that the base from the Bronsted-Lowry definition has to accept H plus in order for it to be considered a base. Now, if you dissolve this in water, the H plus has to come from water itself. So the A minus takes up an H plus. In the process, it increases the number of H's it has by 1, but because it's acquiring H plus and not just H, its charge goes up by 1 unit. It used to be negative in this example, now it's positive. But look what happened at water. Water had to give away its H plus. In essence, water behaves as an acid in this reaction. And by giving away its H plus, the count of H's goes down by 1 unit, but so does its charge. It used to be neutral, and now it's 1 minus. We'll talk a little bit more about that a little later in the lecture. Much like acids, though, there is a list of bases that I kind of want you to be aware of in terms of being strong. Anything you have in the red box right here, metal hydroxides, specifically alkali metal hydroxides. I'll even include the alkaline earth metal hydroxides on this list. Can be considered strong bases. Having the metal oxides or the metal sulfides, those are also considered strong bases because the charge of the anion is relatively high. It's -2. But then anything else, especially if it has funky molecular structures like adenine, one of the bases of DNA, or ammonia, they are considered weak bases, but they are bases. And one of the ways to tell is because of that lone pair, specifically on nitrogen. All right, now we're ready to talk about this idea of the conjugate pair. I kind of gave you an example already with the reaction of a base with water. But with conjugate pairs, the idea is that between the two species, there can only be a difference of an H plus ion. So either you have one less H plus ion than the counterpart, or you have one more H plus ion. So for instance, let's take a look at the following acids. We have hydrochloric acid, perbromic acid, chloric acid, sulfuric acid. To derive the conjugate bases of the following acids, all we have to say is that, well, the acids have to have more H's than the bases. So if we're going to derive the conjugate base, all we do is we rewrite what we have right here minus 1 H plus. So for HCl, that means that you have no longer any H's, but because it was neutral, now the charge goes down to -1. Same idea here. You have HBrO4, so you get rid of one H and the charge goes down by 1 unit. So you'll end up with BO4 1 minus. And HClO3, same idea. The H count goes down by 1 unit. The charge goes down by 1 unit. So you have ClO3 minus. And sulfuric acid, you do have two H's, but to derive the conjugate base, you can only get rid of one H. So you don't want to write SO4 2 minus, you want to write HSO4 minus. So the difference between the conjugate pairs is only 1 H plus. If you go beyond that, you're not looking at conjugate pairs anymore. All right, so all of them are the conjugate base. They have one less H than the acid, and the charge is also one less than that of the acid. All right, so let's take a look at the bases. The bases are going to have one less H than the acids. And so if you want to derive the conjugate acid, simply all you have to do is add an extra H and increase the charge by 1 unit. So for hydroxide, you'll add one extra H, now you have 2. And the charge goes up by 1 unit, so you end up with H2O. For oxide, you can add one extra H and you end up with OH, and the charge goes up by 1 unit, so you end up with OH minus. For sulfide, you add an extra H, now you end up with HS. The charge goes up by 1 unit, so you end up with HS 1 minus. NH3, if it behaves as a base, which it is, it can take up an H, in which case you end up with NH4. But the charge has to go up by 1 unit. Since this is neutral, the charge will become now positively charged. And phosphide, if it acquires 1 H plus, then you end up with HP, but the charge now is 1 greater, so 2 minus. All right, now check this out. These are directly the conjugate acids of the bases that we had written out right here. The only difference between the two species is that H plus, right? One has one more H plus than the other, but that's it. Nothing else is different. So the conjugate acids, you're going to increase, or the amount of H's by 1, you're going to increase the charge by 1 if you are deriving it from the base. All right, so now check this out. Notice that for the conjugate acids we have derived, there's a lot of lone pairs still present. In fact, water can take up yet another proton. The same thing goes for hydroxide, hydrogen sulfide, and hydrogen phosphide. Ammonium cannot do that because the moment it acquires that extra proton, the only lone pair it had is now being occupied in the form of a covalent bond. So that's the only one that basically can't do this process anymore. But these other four can proceed forward. In the case of water, taking up one extra H plus yields H3O plus. Hydroxide yields water. Hydrogen sulfide leads to hydrosulfuric acid. And HP2 minus yields H2P1 minus. And the process can actually continue. In fact, the trend that I usually see with them is that you will continue, and you can, if you have enough H plus concentration in solution, you can actually continue until you get to the +1 species. So for water, taking up an extra proton gets you to H3O plus, but notice that H0 plus, I'm not having you acquire one extra proton. That would be too much positive charge in one small region of space. So the same thing goes for hydrosulfuric acid. You can get to H3S plus, and for the hydrogen phosphide, you can get to what we call phosphine, and even take up an extra proton to go all the way to phosphonium ion. Now, the one thing that you have to be careful about is not to say, well, hydroxide and water, the difference is Hs, excuse me, hydroxide and hydronium, the difference is Hs, so they're conjugate acids. That is not true, because hydroxide only has one H, hydronium has two Hs. That's too much of a difference, so they're not conjugate acids. However, hydroxide and water are conjugates of each other, conjugate pairs of each other. Water and hydronium are also conjugate pairs of each other, all right? But hydroxide and hydronium are not, right? In other words, they have to be right next to each other in the equations. All right, now species like water, hydroxide, hydrogen sulfide, which have H's to begin with, but they can actually take up extra H's, they're behaving as acids, excuse me, they're behaving as bases in this respect by acquiring the H plus. But because they have H's to begin with, they could, under the right conditions, behave as acids. We refer to these substances as amphoteric substances. They can act as both acids and bases. And I want you to be definitely aware of that for water, because water, being a very ubiquitous solvent, um, if you add an acid to water, water will end up behaving as a base. If you add a base to water, water will end up behaving as an acid. And it's that amphoteric aspect of it that will allow us to, portray the acid-base chemistry that we're talking about in this lecture. So yeah, water, hydrogen sulfide, same idea. And all the species here for phosphorus, that basically in between, prior to the ends, those are your amphoteric substances. They have H's, so they could behave as acids under the right conditions. They do have plenty of lone pairs and negative charge, so they can behave as bases as well. Alright, so in the next video, we'll start talking about neutralization reactions and titrations. So I'll see you then.